Hi everybody. In this short presentation, I'm going to talk about power system blackouts. This particular topic became commonly spoken during the last couple of days, but because of the blackout that happens in Sri Lanka on 17th August. Here I will talk about in brief what is a blackout and some particular aspects related to blackout looking at Sri Lankan perspective. Now, a blackout is a loss of power to a region or a country. Here I'm listing few recent blackouts and the most recent one is the one happened in Sri Lanka. There was one in London in August 2019, and you can see that in this picture, the how people trapped in the underground during that power outage. There was a blackout in Venezuela in March 2019, and in July 2012 in India there was a blackout, which which was a very sunny time, hot weather. So all the ACs went down, and people were really suffered from that. Now in Sri Lanka, of course, there were few blackouts in 2016, but afterward there wasn't anything until the recent one. Now, before discuss about blackout, let me discuss the operation of a generator. A generator is one of the key components in our power system. Now, the generator has a rotor, the middle part, which rotates, and a stator, which is stationary and carries three-phase windings, and a DC source is connected to the rotor, so that these are called the poles, and these poles will produce certain amount of fluxes. So what we do is, normally using some prime mover, we rotate the rotor. When the rotor is rotated, the flux that is associated with each and every pole cuts the stator winding and produces a voltage at its terminal. Now, in Sri Lanka, the voltage that is produced by a generator varies from around 6 kilovolt to 20 kilovolt, depending on the size of the generator. Okay, let me talk about something completely different. I'm sure you have seen this one. This is a Zumba dance. And if you look at these three ladies, they are pretty much synchronized. In fact, they are not looking at each other. They are synchronized to the music. Similarly, in the power system, all the generators are synchronized to the frequency. So the generators that we used in power system, we call synchronized generators. Now, whether the generator is in Putlang or whether it's a hydropower plant in Victoria, they are synchronized. So if anything happens to the frequency, every single generator connected to the national grid follow that frequency. Now in Sri Lanka, the frequency is maintained at 50 hertz. So as I said, when the generation is equal to consumption, in second by second basis, generated frequency can be maintained at 50 hertz. However, in reality, the generation will not be completely equal to consumption. If the generation is little less than the consumption, the frequency will drop below 50 hertz. On the other hand, if the generation becomes greater, the frequency will rise above 50 hertz. So in reality, the frequency fluctuates in around 50 hertz, and it's a statutory duty of the utility, that is CEB, to maintain the frequency between 49.5 to 50.5 under normal operating conditions. Okay, Okay, I was previously showing you a generator. Now, generator, which is again shown here, is coupled to a turbine. Now, the turbine is the one which rotates the rotor of the generator. Now, there are different types of turbines. When the generator and turbine couple, they will basically convert one form of energy to electrical energy. Now, what I'm showing here is a steam turbine. Here, inside a boiler, we produce high pressure, high temperature steam using the thermal energy in either coal or biomass or diesel. We convert that into steam, and the steam goes through a steam turbine. And when it is going through the steam turbine, it rotates the turbine shaft, and thus the generator. And the steam that is coming out from the turbine, which is at a lower temperature, is converted back to water using a condenser, and the water is then pumped back to the boiler. So this is the typical operation of a steam turbine. Now, during blackout, one of the common discussion in Sri Lanka is the Norechchola coal power plant. In fact, it's a steam turbine, and what you are seeing here is a simplified diagram of that steam turbine. Now, compared to my previous diagram, this has 4 turbines. One high pressure turbine, one intermediate pressure turbines, 2 low pressure turbines, all connected to the same shaft, and to that the 300 megawatt generator is connected. And you can see that the water going out from the low pressure turbine is going through a condenser. So you can see the temperature entering into the low pressure turbine is high. It emits, it goes out, the water goes out from the low pressure turbine around 140 degrees. After condensing, it comes almost closer to the room temperature. Then it is heated to 120 degrees, and using a deaerator, the oxygen is removed, and it's also heated inside here, and the temperature goes to 160. Then the temperature is elevated using another heater to 270 degrees, and then it goes through the boiler to what we call the steam drum. And you also can see that from the steam drum, there is a superheater connection, which is the high temperature, 540 degrees centigrade, high pressure steam going into the high pressure turbine. And also from the boiler, there is the intermediate pressure loop. So the boiler surface temperature is around 1200 degrees, and the coal is used to heat up all these heaters inside the boiler. I will talk about the function of these different valves and things later on. Now, it's also important to see how the Norechchola coal power plant is connected to the rest of the network, particularly looking at scenarios of blackouts. Now, you can see that the Norechchola has 300 megawatt generators connected to a 220 kV bus bar at Putlang. Then it goes to New Chilau on one side, and on the other side, it goes to New Anuradhapura. From New Chilau, there's a connection to Veyangoda to Kotugoda, to which the Kerawalapiti is connected, and from Kotugoda to Biyagam, and most of the Colombo load is connected to Biyagam bus bar. On the other hand, the New Anuradhapura is connected to Kothmale, and the Kothmale is connected to Biyagam. And all the Mahavalley hydro power plants are connected to the Kothmale. So you can see that it's a mesh network. Of course, there is a 130 kV network also associated with it. Now, this mesh network allows, if a particular part of the network fails from one side, you can still redirect the power using another side to the load center, where the majority of load is is situated. However, these lines doesn't have the same capacity. That's different lines has different uh, power carrying capacity. So if a line section fails, it's more like you are losing part of the load. Now that will be really seen by the generators in Norechchola. Now, then what happened is you will have, for example, assume that for some reason part of the Colombo city was tripped, could be due to a lightning, could be due to any other kind of a fault. Then we have a scenario just before the load was rejected, the generation was equal to load, the consumption or the load. Now the load has come down, so we have more generation, so immediately the system frequency will rise. This is what you see. There is a load rejection here, and the system frequency goes up. Then while the system frequency is going up, all the generators on the system try to reduce their power output. There are automatic governors connected to these generators. So they are basically trying to arrest the increase in frequency, and if successful, you can bring down the frequency, and eventually the frequency will stabilize at some point, and then later you can bring it to 50 hertz. So these kind of events usually happen in power system, but this is not a blackout. This is a temporary oscillation in frequency. But remember, as I told before, as the frequency increases, all the synchronized machines on the network will see this frequency increase, and they will react to that frequency. And that is how they try to reduce their power. That's what we call the govern action of synchronized machines. But in Norechchola power plant, there are more controls. Remember, I said that it is one of the largest power plant on our Sri Lankan power system. In fact, the 3 generators in Norechchola roughly take 1/3 of our peak requirement. So it has few controllers. One of the controllers which comes immediately after the load connected to the generator becomes less, or the rate of change of frequency is greater than certain value, is what we call the fast cutback operation. There's another controller, I will come back to that in a minute. Now this fast cutback operation, what it does is it removes the generator from the national grid, and it then operates on its own. Now, when this generator is disconnected from the national grid as a result of the load disconnection, which has increased the frequency, and the increase of the frequency has triggered the fast cutback, and the fast cutback has disconnected the generator from the grid, then the generator will try to stabilize at what we call the in-house load. So you will see that the speed of the generator will rise, but eventually you reduce the steam by reducing the burning coal, and also by bypassing some of the steam going into the turbine. You basically try to reduce the speed. Now, if the speed goes beyond the 3070 revolution per minute, then the second control operation will come back, which is what I call overspeed protection control. Now, the function of these controllers are to open what we call the bypass valves. Now, there are 2 bypass valves. One is the high pressure bypass valve, and another one is the low pressure bypass valve. Now, the purpose here is, if the load connected to generator is minimum, in the previous case, it is around 20 megawatt or so, you should not produce a lot of power in your turbine. So steam will not go into the turbine. It is bypassed to using the low pressure bypass valve, going back to the boiler and so on. Similarly, the steam coming into the high pressure the valve will be bypassed and send it back. So you can operate your system like this at what we call the in-house load for few minutes or maximum hour or so. Now I will talk about few things happening later on, but this is what the FCB or OPC will do. Now here what I am showing is the temperature of the superheated steam under three conditions. The first one is the normal operation, 300 megawatt is supplied, the superheated steam is at 350 degrees and stable. Now, if they due to a load rejection and the frequency increase, fast cutback initiated, if the load goes to the what we call the in-house load, what it immediately does is it takes few coal mills out, so the burning coal will be reduced, so the steam input will be reduced, so the temperature will try to go down. If it goes down, of course, you cannot make it spinning, so you have to manually somehow control the coal input and make sure that the temperature is maintained somewhat constant value. So you can see that it's coming down, maintain again, coming down, and so on. That is what we call the operating on house load. Now you cannot operate on the house load for longer period. At some point, the machine goes to what we call the complete shutdown. If that is the case, the consequences are much higher. Now, if you can manage to operate your generator on in-house load, then what happens is this is spinning, the generator is spinning, these bypass valves are opening and the loop is nicely working. And the generator produces very low power. And if the national grid comes back, you can connect the generator and slowly increase the power around 2-3 megawatt per minute or so. I can't remember exact rate, but you can connect it and you can bring the machine back to normal operation. Now, if the national grid does not come, as I said, the generator will trip. Then what happens is, the generator not only supply power to the grid, this generator supply power to the boiler feed pump and the condenser extraction pumps. All that power will be lost. So these two will stop. Okay, but what it means is this loop, the water loop will stop. Then the steam inside the drum will evaporate quickly and the drum will have a temperature around 350 degrees. Now you cannot put you have lost a certain amount of water, so you cannot put that water back to the system until the drum is cooled down. That is the reason where it takes a couple of days to restore the coal power plant in Norechchola. So you have to wait until the steam drum temperature comes down, and when the steam down temperature comes down, you can send using these heaters, you heat up the water and put it back to the drum, and you can restart the cycle slowly. So if Norechchola goes out, then we will lose around 900 megawatt. Then the entire system start collapsing because we don't have enough power to supply the load of the country. I thought of also showing you two cases. This was a near blackout happened in May 2007 in the UK, but of course the system recovered. You can see that somewhere around 10:33, generator loss around 345 megawatt loss, and the frequency reduced. Then the second generator loss and the frequency reduced further. As the frequency is reducing, all the distributed generators connected to the network start losing, so the frequency fall down further. Now, one good thing the UK system has, it has a what we call a pump hydro power plant, which is 400 megawatt. Now, when the system is normally running, the which is in generating, in pumping mode, in this particular case, acting as a load, and as the frequency drops, the which quickly goes to what we call the generation mode, and it is more like adding, it's 400 megawatt pumping before, now it goes to 400 megawatt generation. So adding 800 megawatt of power into the grid very quickly. So even though there was a loss of generation of 1582, the which can help to recover the frequency. And finally, they managed to bring the frequency back after 9 minutes of operating the system outside the statutory limit. So if you can do that, even if you can bring the Norechchola back as I showed you, while it is spinning, you can bring the frequency back to the normal case. Now here I'm showing you another frequency plot, which was from the blackout in Sri Lanka in 25th February 2016. Now here, at that time, the fast cutback operation was disabled. Only OPC, which is the overspeed protection controller, was working. So due to a certain problem, I can't remember the exact reason, it was a lightning or something, part of the load was disconnected from the system. So the system frequency rised. And system frequency rise near to 52 hertz. And what happened then? The Norechchola, it was working on, it was connected to the grid, but its bypass valves opened due to the OPC operation, overspeed protection control operation, and immediately reduced the steam. So the Norechchola power output drops. So we have a system where now the system, power generated in the system is less than the load. Then what happened is the frequency drops quickly. When the frequency drops, the Norechchola when came back using its govern action, and when the Norechchola is back, it's a large generator, so it's again start making a low frequency event, and the frequency start fluctuating for a while, and somewhere around this time, all the generators in the system start, dancing to this frequency, that frequency variation, and that makes a huge noise in large generators in hydropower plants and everywhere. So they have manually cut down those generators, and finally system collapsed. And after certain times, we had a island-wide blackout. So I hope that this short presentation gave you an idea what happened during a blackout, and why we talk about Norechchola so much, and why we could not bring Norechchola back on operation quickly, why it took so long to bring it back.